All right, good morning and welcome to Analog Electronic Circuits. This is lecture 5. So, in the last class, we were looking at what one needed for a nonlinear device to be able to get incremental gain, and after a long discussion, we concluded that the incremental Y matrix must be such that what should be the incremental Y matrix? The first row must be 0, y11 and y12 must be 0, y22 must be 0, and this must be as large as possible. And from this incremental matrix, we went and tried to construct what the characteristics of the device itself must be in order that it will have an incremental matrix like this. Okay. And we concluded that if that input port current I1 is 0, right, ideally all that it needs to do to ensure y11 and y12 are 0 is that they must be a constant, that input current I1 must be a constant. A good value for that constant is 0, and it so happens that many devices actually have I1, capital I1 equal to 0. So, if that is the case, then we are in a situation where we can plot the output characteristics, and we said that because the device itself has no sources of energy inside, it must follow that the output characteristics cannot remain parallel to the x axis for all values of V2, and they must eventually dive into the third quadrant. So, so this basically you will get, therefore, in principle you will basically get a family of curves, one for each value of capital V1. Okay. And one of the devices that exhibits this kind of behavior is the N channel MOSFET enhancement mode MOSFET. Okay. And I mean, as far as we are concerned, we are only interested in the IV characteristics of this box, and so this is the drain, this is the gate, and this is the source. And we said that if VGS is less than or equal to VT, the device is off. If the VGS is greater than or equal to VT and VDS is greater than or equal to VGS minus VT, then the current in the drain, which is the equivalent of our capital I2, the drain current is independent of the drain source voltage and depends only on the gate source voltage, and is given by 1/2 mu n Cox W by L times VGS minus VT the whole square. Okay. And consequently, the GM therefore can be written in multiple ways. The transconductance, which is the proxy for Y21, right, is nothing but dou ID by dou VGS, which is mu n Cox W by L times VGS minus VT, which is also equivalent to saying it is 2 ID by VGS minus VT, and there is yet another form. Okay. Right, this VGS minus VT, as you can see, plays a prime role in the determining the current to the MOSFET, and this is often what is called the gate overdrive voltage. And why does it make sense to call it the gate overdrive? Well, any voltage applied across the gate is often called the drive, and it is not merely enough to drive the gate, it must be driven above the threshold voltage. So, the voltage that actually determines the current is not VGS, but VGS minus VT, and therefore, VGS minus VT is called the gate overdrive voltage. Excellent. So, in the triode region, so that where greater than or equal to Vt, but Vds is less than or equal to Vgs minus Vt or less than Vgs minus Vt, we find that two things happen. First, the transconductance, what comment can we make about the transconductance? It is smaller than that we get in saturation, right, and what is the transconductance? It is mu n C ox W by L times V capital VDS, and the output resistance or the output conductance of the MOSFET is GDS, which is mu n C ox W by L times VGS minus VT minus VDS. Does it make sense? Okay. So, for a special case, I mean, you might think that this is not really a useful region of operation, but it turns out that in many cases it so turns out that let us say you are operating the device around an operating point of VDS equal to 0, right, or VDS is very, very small. So, for VDS very, very small, meaning much, much smaller than VGS minus VT. So, what comment can you make in the operating region? Where are we operating on that, in that picture? We are operating somewhere here, deep in triode. Then what can we neglect here? GDS is approximately, what can we neglect? VDS. So, basically this is mu n C ox W by L times VGS minus VT, okay. And what is GDS, by the way? By definition, what is GDS? Is the change in current due to a change in the drain source voltage, okay. And so, what is this telling us? What is what in English, what does that what does this equation mean? Pardon? Yeah, of course, it is not depending on VDS. So, for a fixed VGS, what comment can we make about dou ID by dou VDS? It is constant. So, what does that mean? It is just basically a resistance, right, and the value of the resistance is or the, I mean, it is a the value of the conductance is determined by VGS minus VT, all right. So, basically in deep triode, this basically is nothing but a voltage controlled resistor, and what is the value of the resistance? It is 1 over mu n C ox W by L times VGS minus VT. So, you can think of it as a voltage controlled resistor. All right. This also brings up a very important property of a MOSFET, which we will not cover in this course, but is very useful nevertheless. You can see that when the gate source voltage is less than Vt, right, how does the device behave between the drain and the source? It is an open circuit, right. Now, when VGS is very large, it is a resistance, right. The value of the resistance can be made as small as possible by making W by L very, very large. So, this now enables the MOSFET to operate as a switch, right, as a voltage controlled switch, okay, which is extremely useful in a whole lot of applications. This is just for your reference. We will not be seeing much of that in this course. All right. So, with this in place, our amplifier now looks like this, remember that this is what we had. The device is now has a new symbol. Okay. And rather than keep drawing batteries all over the place, an easier thing to do is to basically say, well, this is RL, this is VB, I will call this, not to get confused with capital VB, and this is VA, this is VI, this is RS. All right. Does it make sense, folks? All right. Now, the question is what do you call, you can see that one of the I would say irritants with this circuit on the right is the fact that we have two batteries, right. Which do you think will be higher? I mean, I do not know if you are able to see this, but if you okay. So, let us say assume that you are looking at the circuit for the very first time. This is clearly a nonlinear circuit. So, the first thing to do is to find the operating point. So, to find the operating point, what will you do? So, whenever you see a nonlinear circuit, the first thing to do is to find the operating point. So, to find the operating point, what will you do? You set all small signals to zero, correct. If we do that, what happens? What do we get? We will basically end up with a circuit like this. So, this is VA, this is some RS, this is VB, this is RL. Okay. So, how will we find the operating point? What is VGS? VA, why? The gate current is 0, so the voltage across the gate is simply VA. So, from the equation of the MOSFET, let us assume that the voltage at the drain is large enough that the transistor is operating in saturation. So, ID is 1/2 mu n C ox W by L times VA minus VT the whole square. What is the drain potential? Yeah. So, the drain potential VD is nothing but, this is the drain, is nothing but VB minus ID times RL. And if you want to ensure that the device is indeed in saturation, what comment can we make about the drain potential? Should be greater than or equal to VA minus VT. Does it make sense? Okay. So, now can you tell me in practice which do you think will be larger, VA or VB? Ideally, what comment can we make about VB? Should it be very large compared to VA or should be very small compared to VA? Large, why? You want to make sure that the transistor is, you know, as deep in saturation as possible. So, for all practical purposes, therefore, VB is going to be hopefully much larger than VA, correct. So, now staring at the circuit, one can say, well, you know, there is obviously an inefficiency in the circuit, and what is that? I mean, if you do not have RL, then you have no load, no. I mean, we know that VB is much larger than VA. So, there is no need to have two voltage sources. One can actually derive the smaller voltage source from the larger one. How do you derive the smaller voltage source from the larger one? You put a voltage divider, right. One way of doing it is to put a voltage divider. So, this is typically called VDD, okay. DD stands for drain, right, and then so all the drain currents eventually find their way there. So, and so we will assume that we derive VA, let us call this R1 and R2, okay. So, as far as biasing, just simply biasing the transistor is concerned, do we need RS or we do not need it? If we just needed to bias the transistor in saturation, this RS is actually coming from the source, it is strictly not necessary, and it may not be, as we will see going forward, that may not be the only location where we can put the source. But as far as biasing the transistor is concerned, the RS is not really necessary. So, this is basically the network, you know, the one of the simplest networks you can think of that will make sure that the transistor is biased in saturation and is ready for action, all right. Okay. Now, so as far as the transistor is concerned, therefore, the incremental Y parameters are, you know, because it is operating in saturation, the incremental model for the transistor looks like this. This is the gate, this is the source, this is the drain, this is nothing but Gm times the incremental VGS, all right. Okay. Now, you know, we need to add the source. Okay. So, the quiescent voltage at this node is VDD plus VDD times R2 by R1 plus R2, and the quiescent voltage at that node is VDD minus capital ID times RL, all right. Now, the transistor is all ready for action. So, what should we should make sure that the incremental voltage at the gate is what, if you want gain, what should be the incremental voltage at the gate? We want to make sure that the incremental voltage here is Vi somehow, all right, okay. And if the incremental voltage there is Vi, you know, what comment can we make about the incremental voltage at the drain? How will we do it? We will need to draw the incremental model. So, what do? We go look at the circuit and replace every element by its incremental equivalent. So, as far as the incremental equivalent is concerned, therefore, you know, what comment can you make about VDD? Becomes a short circuit. So, this is R1, this is R2, this is the transistor, this goes to ground, and this goes to RL, correct. And we should somehow make sure that this node, we should apply our incremental input here, okay. I mean, when I draw the circuit like this, it does not mean that the I mean, you can connect a MOSFET this up this way and you can actually make the circuit work, right. What is this a shorthand for? What does it actually mean? What is the implication of I mean, can I take a physical MOSFET, connect two resistors, you know, from between ground, R1 connects to ground, right, on one side, and R2 also connects to ground on one side. Can I will the circuit work? No, right. Why? Yeah. So, when somebody draws a circuit like this on the left hand side, the implication is that you have to mentally replace that MOSFET by its incremental model, which is this character here. Okay. So, what this means is that as far as the incremental network is concerned, R1 and R2 are in parallel. We will somehow apply the gate voltage Vi there, and this is the controlled source, this is R. This is VO, and this is GM times Vi. So, what comment can we make about VO? Minus GM RL times Vi. All right. So, what in this picture, therefore, the total voltage at the drain, therefore, is the, in a nonlinear network, first thing you do is find the operating point, then you replace every nonlinear element with its incremental model, then you do the, you analyze the incremental network. What kind of network is that? It is a linear network, right. Once you analyze the linear network, you will get all this the voltages and currents at every node and every branch. They all refer to what kind of quantities? They all refer to incremental quantities. So, that is what we have done here. The incremental voltage at the drain is basically given by minus GMRL times Vi. What is the total voltage at the drain? The total voltage at the drain is basically the quiescent value plus the increment. The quiescent value is VDD minus IDRL. The increment is minus GMRL times Vi. So, the total voltage at the drain is VDD minus IDRL minus GMRL times Vi. Okay. All right. So, now the question is, so this is, I mean, the question now is, how do we get an incremental voltage at, I mean, in other words, we want, here is our quiescent circuit, here is our circuit which sets up the operating point. For incremental signals, we want to make it look like this. Correct. So, we want this behavior for incremental signals. Correct. For the time being, let us assume that the source is ideal, it does not have any input resistance. So, or any output resistance. So, what is the, how can we make sure that this voltage here also has an incremental component Vi? The simplest thing I can think of is, say, okay, what happens if I simply connect Vi here? Yes. Why? I mean, what is the incremental voltage at the gate now?
It is the addition of VDD or V potential R2 by R1 plus R2 VDD plus Vi.
Please take a look at this carefully and tell me what is the incremental voltage at the gate? Small Vi, that is what we wanted. Now the question is, can I simply do this? No, why not? Yes, Ralph?
The VI fluctuates more, then this can be also go to it will affect bias. That will shift the tuition point.
Okay, so what is the quiescent operating point now? Whenever you add the incremental voltage, you must make sure that the quiescent operating point of the nonlinear devices is not changed, because you are going to linearize the device about the quiescent operating point. The addition of the incremental source should not change the operating point, correct. So, now if we did this, what comment can you make about the quiescent operating point? So, to find the operating point, what would we do? We make Vi equal to 0. So, this becomes a short circuit. So, what comment can you make about the gate voltage? Gate voltage is 0. So, then what comment can you make about the transistor's operation? Off, right. Vt is greater than 0, okay, and that, by the way, that is what it means to say an enhancement mode device where Vt is greater than 0. So, so if we simply stick the small signal voltage at the gate, for sure the gate incremental voltage at the gate is definitely Vi. Unfortunately, the quiescent voltage is, forget not fluctuating, the quiescent operating point is completely ruined because the gate the transistor is cut off, okay. And why is the operating point changing? This was Vi, okay. Under quiescent circumstances, this node on the left X, the quiescent voltage there is, let us say I do not connect X to, let us call this the gate voltage, the gate G. What is the quiescent voltage on the left? On the left, it is 0, right. For remember, for quiescent operating point, Vi is 0, and so therefore, on the left side it is 0, on the right side it is, this quiescent voltage is R2 by R1 plus R2 times VDD, correct. So, what comment can we make about, so obviously when you short X to G, what happens? Why does what happens when you short node X to node G? Nothing, no violation of anything. What happens? The voltage, current is being drawn from the node G, and therefore its voltage will drop, correct. Because the source is ideal, it will drop to 0. If the source was not ideal, what will happen? Let us say the source had a source resistance of Rs. What will happen? Some current will flow through Rs, the voltage will drop, but it will not drop to 0, okay. It will drop to Rs parallel R2 divided by Rs parallel R2 plus R1 times VDD. At any rate, the quiescent operating point is going to change, right, which is not intended, because we bias the transistor at a desired operating point, and the act of putting the incremental voltage source at the gate has gone and changed that operating point. Is this clear? All right. So, the root cause, as you can see, is that the potential of X and the potential of G are not the same. If they were the same, then shorting the two would make no difference to the operating point. Is that clear? So, in principle, what should we do? between x and d, I mean the potential of x is 0, the potential of G is VDD times R2 by R1 plus R2, there is a difference between the two. Okay. So, if we short the two, current is going to be drawn. If you want to prevent current being drawn from the gate node, the potential of x must be the same as the potential at G. So, in principle, what will we do? In principle, we want to equalize both the potentials, right. If you want to equalize two things, you either pull G down or pull x up. Okay. Pulling G down is no solution because that is going to kill the transistor. So, the only solution is to pull x up. So, in principle, what will we do? We will put a battery of value VDD times R2 by R1 plus R2. This is in principle, right. If we did this, then the quiescent operating point is not going to change, correct, and we can go about our incremental analysis. How will the incremental network look like now? On the left side, what must we do? Look carefully. The source is changed now. Yes, how will the incremental network look like? Huh? Same as before. So, there is now a source resistance which I do not see in the incremental equivalent. Where will I put that? Yeah. So, because we have an RS, this will be the incremental equivalent, and therefore, what will be the gain? What will be the incremental gain, or what will be the incremental output? Yes? Okay. So, what will be the output voltage now therefore? Into R1 parallel R2 by RS plus R1 parallel R2. Okay. So, as an aside, what comment can we make about R1 parallel R2? How should we choose R1 parallel R2? If you want to make sure that the gain is not affected very much. Yeah. So, must choose R1 parallel R2 to be much larger than RS. Okay. Then this will approximately be minus GMRL times P. Okay. All right. So, stare at this picture, therefore, let us come back to this picture here. Okay, the whole idea we put the potential divider on the gate side was to eliminate a battery. Okay. Now, it seems that we have come back to a battery. Okay. So, how do we, sir, what do you think, I mean, and what do you think we can do to solve this problem? What is the current being drawn from the battery? What is the quiescent current being drawn from the battery? How much current, how much DC current is flowing through the battery? The red battery. Yes, you? 0. Why? The two potentials are the same, all right, okay, all right. So, there is no current being drawn from the battery, Okay, and remember we also talked about how to realize a a battery with a capacitor. What did we say? Yes, an infinite capacitor, charged to a certain voltage is equivalent to a battery charged to the same voltage, and in this particular case, even if that infinite capacitor is replaced by a finite one, right, uh, notice that there is no current being drawn from there is no DC current being drawn through the going through the battery, correct. So, therefore, in principle, even if I replace that capacitor by a finite capacitor, as far as the operating point, I mean the voltage across that capacitor will not change, all right. So, for the time being, let us assume that we replace this by an infinite capacitor, all right. So, what will be the voltage across the infinite capacitor? Voltage across this infinite capacitor. What is the what is the purpose of that infinite capacitor? What is it planning? What is it doing? It is replacing a battery of voltage VDD times R2 by R1 plus R2. So, what is the voltage drop across that infinite capacitor therefore? What is the potential on the right? VDD by R times R2 by R1 plus R2. What is the potential on the left? What is the potential on plate X? What is the quiescent voltage at node X? 0. So, what is the voltage drop across that capacitor? This voltage is going to be VDD times R2 by R1 plus R2. So, all that the capacitor is doing is behaving like a battery with a voltage VDD times R2 by R1 plus R2. So, what happens in the incremental equivalent? The incremental equivalent just simply becomes a short circuit. Okay. All right. So, we will come back, of course, in reality it is not possible to have an infinite capacitor, all the capacitors will be finite. So, we can't make an infinitely large capacitor. So, we will say we will replace it with a sufficiently large capacitor, and then the obvious question that comes up is how large is large and what does large mean, okay, all right. And another kind of a little bit of a problem with the circuit here is that the load, what comment can we make about the current through the load? Is it a DC current? Is there a DC current flowing through the load? Yes, okay. So, it turns out that in practice many times it is not permitted to have DC current through the load. An example of such a load is a loudspeaker, right, because there is some it's a coil around a magnet and so on. It does not make you will saturate the magnet if you have DC current flowing through the coil, and therefore, in many cases what happens is that you are also constrained to make sure that the load does not have any DC current flowing through it, okay. And it also turns out that oftentimes you have yet another constraint, and that is the load is one terminal of the load is grounded, you do not have access to that terminal. So, in other words, you have a load like this, let us call this RL1, okay, and you also cannot have DC current flowing through RL1. So, what comment, how do we therefore connect RL1 to the output of the amplifier? One way of doing it is to simply short those two. What will happen now? DC current will flow through it. Why is DC current flowing? Because before you connected, the quiescent voltage on the right is different from the quiescent voltage on the left. So, how will you prevent current from flowing? You, I mean, in principle you will put a battery of voltage VDD minus ID times RL, right, and that battery, so is going to be like this. So, this is VDD minus ID RL, okay. And how do you realize the battery? You replace it with an infinite capacitor. All right. Now, what comment can you make about the has the quiescent operating point of the transistor changed? The quiescent operating point of the transistor has not changed, and the only thing that has what has changed then? What comment can we make about the incremental gain now? There is also an additional term RL1. So, what comment can we make about the gain now? RL parallel RL1 times R1 parallel R2 times Vi, and therefore, this is approximately RL parallel RL. So, is this gain larger than before or smaller than before? It is smaller than before, and that is the penalty to be paid. See, whenever you have you have constraints, correct, you have to pay something to be able to overcome those constraints, all right. So, here you wanted the load to be grounded, you wanted no DC current to flow through the gate through the load. I mean, that basically means that you are asking for something. If you ask for something, you must be prepared to pay something, and that pay something is equivalent to decrease the gain, all right. Now, we have seen that an infinite capacitor for incremental signals, an infinite capacitor charged to a voltage VB is equivalent to a battery of voltage VB, and therefore, for incremental signals this looks like a short circuit, okay. So, whatever you can do with voltage you can do with current, whatever you can do with a capacitor you can do with an whatever you can do with a capacitor you can do with a what is the, if I say voltage is to current as capacitor is to, a capacitance stores charge, right, okay. Inductor stores energy in the form of flux, correct. So, a capacitor can be left open, an inductor must always be left shorted, right. So, an inductor which is carrying a current, I am assuming that there is some path here, an inductor which is carrying a current I is equivalent to a, therefore, a current source of value I, which in the incremental is an open circuit. So, what do you notice between the I mean, so an infinite capacitor is open in the quiescent, in the circuit that finds the quiescent operating point, the capacitor is open, whereas in the incremental network it is a short circuit. An inductor, an infinite inductor on the other hand is a short circuit in the quiescent network, but open in the incremental network, right. So, these are extremely I mean these are useful things to know, right. So, one way we saw that when we added this RL1 which was grounded and we did not want any current to DC current to flow through it, we had to couple it with a infinite capacitor and thereby lose gain. Okay. Why are we losing gain, by the way? The incremental current coming from the transistor, if you didn't want to lose gain, you had to ensure that all that incremental current flows through which of the resistors? Through RL1, right, but now part of it is flowing through RL, right. Okay. So, if you want to fix this problem, what do you think you can do now that you know about inductors? You replace RL with an infinite inductor, or you can put R in, as he suggests, you can put the infinite inductor in series with RL. So, basically if you put an infinite inductor here, then in the incremental network the inductor will become an open circuit and all the current will pass through RL, right. Of course, the practicality of using an infinite inductor is a different matter, but at this point this is an in principle argument. Okay. Nobody does this usually, because the inductors can tend to become physically very big. Okay. And by the way, this is not the only way of coupling the input source to the gate, right. Can somebody tell me another way of inserting the, making sure that the gate voltage is Vi incrementally? In the same network, if we didn't want to use transformers, okay, we will stop now, we will discuss tomorrow.